This is the second video in the anatomy and physiology of the kidney. And in it, we're going to begin to look at how filtrate is formed, and we're also going to start to look at the process of reabsorption. So that's what we'll do. And this is an interesting little graphic that you can look at. And some states in the West are actually having problems with people. They believe it started with long-haul truckers peeing in jugs and throwing those jugs out onto the side of the road. And this one was kind of interesting, wasn't it? And so a trucker was found dead in Utah. His pants were around his knees, and he was trying to pee into a jug. Probably why he got into the wreck in the first place, wouldn't you think? All right, well, what is it that we see here? And you should say, well, okay, this is the glomerular capsule. And in addition, what you can see is the juxtaglomerular apparatus that's there. And so there's the renal corpuscle. The glomerulus is here underneath part of the visceral capsule. And then there's the glomerular capsule on top of it. Again, I want you to remember, this is like the fist pushed into the balloon, a layer that's right on top of the fist, and then a layer of the balloon that's away from it with some air in between. In this case, what's in between is the filtrate. And then there's that juxtaglomerular apparatus that's so important. And now what we're doing is we're taking a piece of this and blowing it up so that we can look at it a little bit more closely. And there you can see the glomerular capillary, sorry. And what kind of a capillary is this guy? And these should be a clue for you, although they're not the greatest depiction in the world. This is a fenestrated capillary, which is more leaky than a typical systemic capillary, which is just a continuous capillary. I want you to remember that these aren't complete holes. There are two pieces of phospholipid bilayer that are squeezed together so that there's no cytoplasm there in between. And that does make it easier for stuff to get out and get across. Okay, the filtration membrane actually consists of three different parts, a part that you can't see here. And so the endothelium of the glomerulus, as we just mentioned, and there it is, there's that endothelium. There's basement membrane here that you can't quite see. I guess this is supposed to represent the basement membrane. And then finally, on top of that basement membrane, what you can see is you can see the visceral layer of the glomerular capsule. And this visceral layer is a number of modified, highly branching epithelial cells. And so here's that epithelial cell. It's been modified, and it branches a whole lot, and it has these things which are called podocytes, these processes, and you can see how they kind of interdigitate. Here you can see another picture of what we just talked about. Here's our fenestrated capillary. And this one, you really can't see that basement membrane, but then you can see a couple of different podocytes with those foot processes that exist. And again, they interdigitate. Here's a different depiction of the glomerular renal corpuscle with the capsule and the capillary. In this particular case, rather than using pale green arrows to illustrate the filtrate, it's being illustrated with these blue arrows. And so you see formation and movement of the filtrate, and it's moving into, I hope you remember that this is the beginning of the proximal convoluted tubule. So there you go. And here you can see some detail of that filtration barrier again. And so you can see that we're going to have to pass across the endothelium. And so there are actually some gaps in between those endothelial cells as well as the fenestrations. And so this makes this thing nice and leaky. And then we have that basement membrane, which relatively is thinner than what they're showing you here. And then finally, we have these filtration slits that exist between those foot processes of the podocytes. Again, these are interdigitating, and they could come from different podocytes. They're not necessarily the same podocytes. And then what component of blood tends to be too big to get into the filtrate? And again, Same thing for interstitial fluid, same thing for lymph, and so you should say, okay, the proteins tend to be too big to get across, and so they generally aren't part of the filtrate. But again, these capillaries are leakier than normal, and some protein can escape through, but we're going to try and prevent that as much as possible. Remember that proteins tend to be negatively charged, and so the basement membrane also has a negative charge, and you know, like charges repel one another, and so this too helps to keep protein from getting across and becoming part of the filtrate. So there you go. Here we can see another depiction of that filtration barrier that we have here. And so again, we start with the endothelium. Here is the blood in that glomerular capillary. And here's a white blood cell. Here's a red blood cell. There are some of those proteins. And again, I want you to remember the proteins do tend to carry a negative charge on them. And then we have the basement membrane in between, which also has a negative charge, like charges repel. And then we have the filtration slits that exist between those podocyte foot processes that we have all along here. And so on this side, this is where we have the filtrate being formed and moving through. Okay, well, the blood perfuses the glomerulus and fluid is pushed across. And it's formation of filtrate the same way that we formed interstitial fluid across a systemic capillary. What is it that gets pushed across the filtration membrane? Well, yeah, filtrate. What is filtrate made up of? And not surprisingly, the vast majority of the filtrate is water. But then we also have lots of solutes in there. You know glucose gets across. A lot of ions get across. All those important ions that we've talked about: sodium, potassium, chloride, calcium, magnesium, amino acids, waste products including ammonia, urea, uric acid. Hormones and vitamins can also get across. And some protein does get over there. Not a lot, but some. None of the larger proteins will do that. And here you can see, again, this is our renal corpuscle. Here's our glomerular capillary, and we're pushing filtrate out. And what is it that these arrows represent? And what you should say is these arrows represent the Starling forces. That's what they are. And so the Starling forces are, again, include hydrostatic pressure. Hydrostatic pressure inside the glomerular capillary. The hydrostatic pressure in the glomerular capillary is pushing fluid out into the space. That's what it's doing. Well, then we have the osmotic pressure, largely due to the proteins in here, but due to some other solute, trying to keep the fluid in. But then since there is fluid out here, there's also going to be hydrostatic pressure in the capsule. And so now this is the hydrostatic pressure, which is working against the hydrostatic pressure inside the glomerulus itself. Well, we add all of them up, and what do we come up with? Well, we come up with the net filtration pressure. And in a healthy person, the net filtration pressure is always going to form filtrate. And so the filtrate is here, and it's going to be pushed along, and here it starts to enter the beginning of the proximal convoluted tubule. Well, what are the differences between filtrate and blood plasma? And so you should say the major difference is, absence of big proteins in the filtrate. And that would be true. We've got different categories of substances in the blood based on how easily they can move across. And so some stuff is freely filtered. And so again, not surprisingly, well, that's going to be water, glucose, and all those other things that we talked about, including water-soluble vitamins. So that would be, the water-soluble ones are the B complex and C. Water-soluble. And so when you take a vitamin supplement, you actually pee out a lot of the water-soluble vitamin. Some hormones, a bunch of ions, but not the protons. They're not freely filtered. And then you have stuff that's not filtered, and again, none of the formed elements. No red blood cells, no white blood cells, and no large proteins. And then we do have some things for which there is limited filtration. And now here you can see, oh, look at the difference in concentration in blood versus concentration in the glomerular filtrate. Sodium, potassium, chloride, calcium, all the same concentration. Glucose, same concentration. But now when we look in the filtrate, we don't find any albumin, which is quantitatively the protein that you have the most of in the blood, and you don't find any red blood cells, and you don't find any leukocytes. The osmolality is actually just slightly less than 300 milliosmoles, but you can see that it's the same for both the filtrate and for the blood itself. This is a nice scanning electron micrograph of what? What are you looking at here? And so you should say that this guy right here is a podocyte, and then here are those extensions and the foot processes of the podocyte. And here you can see how they interdigitate with the foot processes of other podocytes. So the red also represents those extensions of podocytes. And you can't really see it underneath there, but what is underneath there is that fenestrated glomerular capillary. And so this is actually inside the capsule, which is where the filtrate would be. Okay? All right. Well, what is net filtration pressure? This is a really, really important concept, and you've got to understand that net filtration pressure. The net filtration pressure is the combination of the hydrostatic pressure inside the glomerular capillary, the osmotic pressure in the glomerular capillary, and the hydrostatic pressure in the capsule. So that's capsule, not capillary. So it's the sum. And what you have to remember is that these two, they're negative. So go ahead and complete this table now. And so if you were having any difficulty, you should have come up with 15 here as the net filtration pressure. And since this is pressure, what are the units of measurement for this? And you should say millimeters of mercury. And that's, I don't write very well, do I? I'm bad enough even if I have a pencil or a pen, but using this little thing, wow, that's bad news, huh? So there you go. It is in millimeters of mercury. You should have come up with 25 here, and 8 here, and 15 here. So again, this net filtration pressure is an important concept, as is glomerular filtration rate. Well, you know what a rate is. Rate includes a unit of time. And so the glomerular filtration rate is the volume of filtrate in either milliliters or liters that's formed per unit of time. And it's almost always milliliters per minute or liters per day. So that's usually what we do. An average for a young healthy person would be 125 milliliters per minute. So 125 milliliters of filtrate formed each minute. Probably shouldn't bother to do this anymore, right? There we go. Well, there is, in fact, a relation between the glomerular filtration rate and the net filtration pressure. And it's the net filtration pressure which determines the glomerular filtration rate. And so we have this direct relationship. The higher the net filtration pressure, the greater the glomerular filtration rate. Okay? Now, the net filtration pressure, again, is critical. If it drops too low, under 45 millimeters of mercury, GFR drops to 0, you're not creating any urine. Well, that means you're not reabsorbing good stuff, and you're not getting rid of the bad stuff, which quickly will become toxic and will be a problem. And so that's why the kidney is essential to people. Well, you know, if the net filtration pressure is going up, reabsorption of substances is going to become less effective. We don't reabsorb as fast as we could before. That's because the filtrate is moving through the nephron faster. So we don't reabsorb as much as we want to. And so that means it's important that we regulate the glomerular filtration rate. We don't want it to drop too low or you die, but we don't want it to get too high either. And so here you can see some data for net glomerular filtration rate. So read the y-axis. What are the units in this case? So good. So now you can see we're looking at glomerular filtration rate in liters per day. And you can see that normal looks like it's about 180 liters per day. Did you hear that? The filtrate is formed from what? Blood. How much blood do you have? 5 liters. How much filtrate are you forming? 180. Holy mackerel. So you can see what's going on here. What is the effect on glomerular filtration rate of a change in mean arterial pressure between 80 and 180? And you say nothing. When you look at that, you can see that the body is pretty darn good at maintaining the glomerular filtration rate pretty constant between a very wide range of mean arterial pressures. Mean arterial pressure of 80 is very low, 180 is very high. For you guys, that means that you're doing some pretty intense exercise as you do that. Well, why is it that an MAP below 80 millimeters of mercury results in a decreased glomerular filtration rate? What's happening is, as the mean arterial pressure is decreasing, you're getting a vasodilation of the afferent arteriole, trying to let more blood into the glomerular capillary to maintain that pressure, the glomerular hydrostatic pressure. Well, at this point, once we get down to here, the afferent arteriole has reached maximal vasodilation. It can't vasodilate anymore. And so now, as MAP continues to drop, now GFR also starts to drop. So there you go. And so that's really what's reached at an MAP of 80 millimeters of mercury. I gave you the answer before I gave you the question. Oh well, what are you going to do? So again, this is maximum vasodilation of the afferent arteriole. Well, how do you know that the vast majority of water in the ultrafiltrate is returned to the plasma? And so pause it, write down a thought as to what that is. And again, what you should have said here is, well, you're forming 180 liters of filtrate per day from the blood. You've only got 5 liters of blood. And so the vast majority of this, more than 175 liters, is being reabsorbed and returned to the plasma. So there you go. Okay. So as MAP decreases, what adjustment is made to maintain, first, net filtration pressure, and secondly, glomerular filtration rate? And again, earlier, I pointed out to you that the afferent arteriole actually is bigger than the efferent arteriole, and we've got a better ability to vasodilate, vasoconstrict this afferent arteriole to meet needs. And so that's what we're going to do. And so this is really, because it's due to the smooth muscle that's located there, this is myogenic, and it's happening here in the kidney itself. So this is a renal autoregulation. Renal autoregulation. Now, so this is, see, normal blood pressure. If we have an increase in mean arterial pressure, what do you think we would do in that case? Well, now what we're going to do is we're going to vasoconstrict the afferent arteriole and let less blood in here. Less blood coming in is going to prevent that hydrostatic pressure on the glomerular capillary from rising too high. So that's important. That's important as we do this. And again, it's myogenic, because the vasodilation, vasoconstriction is related to smooth muscle. So smooth muscle, myogenic. But again, it's auto-regulation. The smooth muscle is going to relax in response to stretch, decreased stretch, decreased stretch, decreased. And it's going to contract in response to increased stretch. So blood pressure going up, there's going to be an increase in stretch over here. The other thing that helps here is what's called tubuloglomerular feedback. And now this starts to involve those macula densa cells of the juxtaglomerular apparatus. And as we said earlier, an increased glomerular filtration rate means stuff moves through the nephron faster. We don't reabsorb quite as well. And so when we get over here, we're going to have a high concentration of sodium chloride that can in fact be sensed by those macula densa cells. So increased fluid in the tubule, increased sodium chloride in the fluid, less time for reabsorption. And so again, the macula densa cells, right there, they sense this higher level of sodium chloride, so the kidney essentially is saying, okay, fluid's going through too quickly. And so we need to adjust to things. And so they release a signal which is going to cause vasoconstriction of this afferent arteriole, decrease the fluid coming into here, decrease the glomerular filtration rate. And so again, vasoconstriction results in a decreased hydrostatic pressure in the glomerular capillary. The myogenic response, the tubuloglomerular feedback are happening right here within the kidney itself. And I just gave you a big hint. And so for that reason, this is referred to as intrinsic. It's inherent to the kidney. That's what's going on here. Okay? However, we also have extrinsic control of the kidney and of glomerular filtration rate. And what protein from the kidney is going to do that? Well, you should be able to kind of figure that out. If we have an increased sympathetic nervous system activity, we get vasoconstriction of these afferent and efferent arterioles. As a result, we get a decrease in blood flow to the glomerulus. And so now, oh, look at that. Here it is, renin again. We've talked about renin over and over and over. The renin is coming from those granular cells of the afferent arteriole, part of the juxtaglomerular apparatus, and it is indeed part of the renin angiotensin aldosterone system, which is that salt-conserving system that we talked about. And so the increased renin means increased angiotensin 2 coming out of the lung. And that increased angiotensin 2 is going to cause a contraction, and we end up with a decrease in filtration. Decrease in filtration, because angiotensin 2 is a potent vasoconstrictor, a potent vasoconstrictor. On the other hand, the end result is that decreased filtration means a decreased glomerular filtration rate. Okay. On the other hand, we can also increase atrial natriuretic peptide, which is a salt wasting system. That's going to mean a decrease in renin, which will mean a decrease in angiotensin 2. And so now as a result of that, we're going to get a relaxation of the cells, and we're going to get an increase in filtration and increased glomerular filtration rate. And so you can see that we've got two systems that help to try to maintain that glomerular filtration rate at about 180 liters per day, an intrinsic and an extrinsic mechanism. Okay? Well, how does a glomerular filtration rate affect urine production and hence blood pressure? Well, as you can imagine, greater glomerular filtration rate, greater urine production, we're losing water, and it's going to tend to hold blood pressure down or even reduce it. Okay. All right, well, here again we can see part of, here is the capsule. And here's the filtrate that's been formed here. This is the proximal convoluted tubule. And so I want you to look at this, and I want you to think about what is it that's going to be helpful here in forming the urine. And I don't just mean the filtrate, but I mean the final makeup of the urine, the concentration of the urine. And so again, much of the nephron is made up of simple cuboidal epithelium with microvilli. Okay, and so that plays a role in what's going to happen here. Then we also have what's referred to as paracellular transport, and as you can see, that's actually movement in between these epithelial cells. These epithelial cells aren't tied as tightly together as epithelial cells of some other barriers like your skin, and so some stuff does indeed get through there. Well, we also have proteins that we stick into the membranes. And so we get transcellular transport, and that's movement that goes through the epithelial cell. And that's going to involve different proteins that we need to have here that help. We have this peritubular capillary, and it has a low hydrostatic pressure and a high colloid pressure, which means that it's going to help to draw fluid into the inside here and help to reclaim some of that stuff. And then again, we have more transport proteins that are on the basal surface of these cuboidal epithelial cells that we have here. And so all of that stuff helps to contribute to the final makeup of the filtrate and hence the urine, what it's going to look like. All right, well, look at what this is all about. What do you know about glucose and filtrate? Well, you should remember that glucose is freely filtered. And all the glucose tends to go across into the filtrate, but glucose is good stuff and we want it back. So pause this, write a quick explanation. All right, and so again, as we've looked at before, you know that there's a really high concentration of sodium in the filtrate and a low concentration of sodium inside these epithelial cells. Sodium is going to go down its concentration gradient, move to the inside. And as it does that, it can help to transport glucose through symport across into the inside. And again, we've seen this multiple times now. This is a sodium-glucose linked transporter. And so glucose is using the sodium concentration to move into the inside of the cell. And then the glucose will move through a GLUT molecule to get out of the cell on the other side, move into the interstitial fluid, and then from there into the blood and be carried back and returned to your body so that it can be used as an energy source. But what didn't they include in the basement membrane here? And so if you don't do it, then you're going to lose points here. Sorry about that. Lance, was the desktop a little bit better that time? And so what is it that should be here that isn't? And what you should have said is what should be here would be those sodium-potassium pumps so that we can pump the sodium out and keep the concentration of sodium in the cell nice and low. We don't want much sodium here. Okay? How much glucose is in the tubular fluid after reabsorption? Well, again, in a young, healthy person, none. But again, you know that you can eat so much sugar that you overwhelm these guys, and some of the glucose gets by the SGLTs before it can be reabsorbed. And in that case, you would indeed experience some glycosuria. And so Easter is coming up. I don't know how much candy you guys plan on eating, but if you can get some glucose strips, what I'd like you to do is eat a whole lot of candy, measure the glucose in your urine, and see if you can actually overwhelm your SGLTs and get a little bit of glucose in your urine. And that'll be your lab for the week of Easter. All right, where does most sodium reabsorption occur? Well, again, we said that most reabsorption occurs in the proximal convoluted tubule. They have more highly developed cuboidal epithelial cells with more microvilli. And so that's where the majority of the sodium transport is occurring. Here you can see these sodium transport proteins. And so they might be like leak channels. They move across. And then we have the sodium-potassium pumps. So again, out here we have a really high sodium concentration. In here we have low sodium concentration. So sodium diffuses in, going down its concentration gradient. And then again, the pumps are indeed active, and so they require ATP in order to move the sodium out. Is sodium, like glucose, 100% reabsorbed? The answer is no, it isn't. It's 65% reabsorbed in the proximal convoluted tubule there, but then we can adjust it and reabsorb even more. What two hormones can alter the amount of sodium that is indeed reabsorbed? Well, the biggie that you should have mentioned is the aldosterone. And so aldosterone, here you can see it. And now we're in a principal cell. The principal cells are found either in the collecting tubule or the collecting duct. And so that's where we find the receptors for the aldosterone. And then aldosterone is going to have these cells insert more sodium channels so that we reabsorb more of the sodium before it can escape. And so a little bit of that happens in the distal convoluted tubule. But again, the aldosterone has the biggest effect on the collecting tubule and the collecting duct. Okay, and then the other hormone that plays a role is atrial natriuretic peptide, which is sodium wasting. It's going to inhibit aldosterone, and so now there will be fewer sodium channels, and you'll have a saltier urine in that case. And if anybody wants extra credit, make your urine really salty, taste it, let me know how salty it really turns out to be. Okay, and what is it that's being shown here? Again, we're looking at principal cells. Oh, look at that. What are we trying to reabsorb in this particular case? Yeah, we're trying to reabsorb water because these are aquaporins. Aquaporins. Here you can see a water channel, and water moves across via osmosis. Okay, and so osmosis is just simply a special case of diffusion. Again, in adult males, glomerular filtration rate could be as much as 180 liters per day. And so we're filtering the plasma 65 times per day. 165 liters is reabsorbed. And again, the ADH is going to help with that process. Okay, so some of it is reabsorbed here. We have aquaporins in the descending limb, which are not affected by ADH, so not affected. The interstitial fluid here is very, very, very concentrated, and that's going to help to draw out water as the filtrate is moving down through the descending limb. And so 65% of the water absorption is occurring in the proximal convoluted tubule. And again, that's obligatory, and that's because the ADH has no effect here. ADH has no effect. Okay. And then the aquaporin number, again, in the proximal convoluted tubule is not affected by the levels of ADH. I don't know why I have all these little lines in there. You can just ignore them. And then we also have what's referred to as facultative water reabsorption, and it is indeed affected by the ADH. And in the distal convoluted tubule, the collecting tubule, and in the collecting duct. And that brings us to the end of video number 2. And in video number 3, we'll look a little bit more at reabsorption of some things, and we'll see how is it that you create low volume, high concentration urine? How is it that you create high volume, low concentration urine?